So this is what you have to do. I had shared the file with you, right? So we have the library. I have a data over here, right? And based on the data, you have to do two things. First, you have to perform exploratory data analysis, and second, you have to build up the model, right? So here is your information, and here is your target. So perform the exploratory data analysis. How these factor? What are the statistical analysis of it? Do the visualizations, plot the data, right? Find out correlations, find out how categorical values are related to each other. For example, how geography is affecting the exit, how gender is affecting the exit, right? So these things find out, and thereafter build a predictive model which can predict the exit. Can you access the file that I shared with you?
Yes, sir.
Okay, so please just work on it. Whatever you think, like whatever you feel like, okay, this is a correct, incorrect, just try to do this. Okay, whether, and thereafter, once we do it, thereafter I'll tell you the process so that you know it can be better. I can tell you now also, but you know it will be kind of a normal. I told everything and you'll forget everything. I don't want that. First of all, you should try, and thereafter I will explain. So can you let me know what is your first thing that you did? Whenever you have a data, what we do first? First, we check the shape of it. All right. So we have 10,000 samples. Second, we check the what are the columns do we have? Okay. So based on this, according to our things, like suppose I have to do EDA, then for EDA, what are the columns which are important? And obviously for the EDA, row number is important, customer ID is important, surname is, these row number, customer ID is not important. Okay, row number is not so important, customer ID is not so important, surname is also not so important, right? Like whether someone will keep using the service or leave the service, these guys are not so important, right? So what we do, we just keep those things which are important and remove those columns which are not so important as per domain understanding. So as per domain understanding, these guys will remove from here. Okay, this is the first thing we do, and update it into a new data frame called DF1. All right. Next. Tell me. Next, what we should do?
The value counts for.
Right. We can do the value count, but before that, we should also do the data types check. Okay, so if these are the data types, like these are object, these are integer, right? So with that, we can find out that we have only two non-numerical columns. Okay. Next, when it comes to analysis, it's a univariate or bivariate. Okay. So univariate analysis helps us to understand the distribution of data. Okay, like for example, K-Disco is a numerical value. So here we can do what? Before that, we should also check the null values. So we don't have a null values over here. So we will take the K-Disco, DF of K-Disco. And the plot that we can perform over here is histogram plot, just to understand the distribution of it. So this is a normal distribution, okay, sort of normal distribution, but it is not highly normal, but yeah, it is good. It's not that skewed. So this data is fine, okay, we don't have any problem in it. It's not like that we have any outlier or something like that, okay. So if suppose it is, or to check the outlier, we can do one more thing, which is called box plot, right? Okay, so we don't have much outliers. Some outliers are there on the lower hand side, but they are also very close to the lower limit. Okay, they're very close to lower limit. They are not. It's not like that they are very far away. So we can use them as it is. Thereafter, we have a geography, right? So I'll just check the geography over here. So it is a categorical column. So we will do what? Dot value counts. Okay. And then we can do what? We can plot it, right? So dot plot dot bar, just to understand the distribution. So it says that yeah, we have more data from the France. Okay, so it's like France is something which is getting a biasness over here. Okay, that means we have almost 50% data from the France and there's 50% Germany and Spain, right? So that is what we have. Next column we have gender. So let's talk about the gender thing. Okay, so this is not so much skewed, or you can say it is not biased. Okay, male and female both are having almost same number of counts. Then again we'll check what are the data do we have. Now age, right? So age is continuous. So df1 age dot histogram. Okay, so some people are there who are having a from higher age groups. Okay, they may be the outliers. Okay, so we can also use dot plot dot histogram. That is also fine. Okay. So what we do, we can just plot over here the box plot. Okay. Yeah, as I said, there are some outliers are there in the upper age. We have people, most of the 98% of the people are from age below close to 65. Okay, some people are above 65. They are very less in count. You can find out the percentage. So can you let me know what are the people, the percentage of people, percentage of data where, okay, percent of data where, or you can say with age outliers. Okay. So can you just try to find out the percentage of data with the age outliers? What should we do over here? Please tell me.
So first we'll find the median, mean, and then variance and standard deviation.
Right. Correct.
Then we'll find the lower fence and the upper fence. And like for the first standard deviation, then for second standard deviation and third. So based on that, like if
Nice.
data.
Nice. Yeah, that's what we can do. Or if I want to use it through this quantile, that's what also we can do, right? So for example, over here, let's say what is like quantile 1?
1.5.
Correct. It's very nice. Okay, so we can do what? df1 age dot quantile 1. As Ananya said, we can do it through
standard deviation method.
Or we can do it through this process. This is quantile 1.
And then quantile 3.
Right, correct.
Q3 minus Q1, then give you the IQR value.
Right, Q3. Then we can have the IQR value over here.
For 75, their second line is 0.20.
Q1, right? Then upper fence will be equals to what? Q3 plus 1.5 times of IQR. Nice. And then lower fence will be equals to what? Q1 minus 1.5 times of IQR. Right. And then we can just find out. So to find out, we will do what? df1 age. Okay. df1 the age column higher than Q3. Okay. Or sorry, higher than Q3 or
lesser than
Q1. Correct. Thank you.
In second line, we have to do 0.75.
Right. Thank you. Okay. So now based on this, if I will try to find out the sum of it, so it will be, we have age capital.
So the IQR formula, sir. Q3 minus 6 equal.
Q3 minus Q1. Yeah, right. Okay, so it seems to be okay. It's not Q3 higher, age value higher than Q3 or lesser than Q1. Q1 is 0.25, Q3 is 0.75. 3 plus 1.5 times of QR. Okay, here I should use upper fence and lower fence. I did a mistake. This is upper fence and this is lower fence. This is close to 359, right? So it's like print percentage of data as outliers. So it's print divided by 100. So this will be close to, okay, this is 3 divided by 100. If I'm doing something wrong over here.
So it would be 10,000. So like I think
Yeah, right, 10,000, right. Okay, so it's close to 0.3, right? Or if I multiply this thing by 100, I'll get the exact percentage. So this is 3.5 now, which is actually high, right? It's like kind of we can't remove those 3.59% of samples. Okay, so we have option of we can clip them. We can clip them to the upper limit. Okay, but right now we don't clip them. We just use them as it is. Later on, while model tuning process, we'll try to clip them and see if performance is improving or not. Right. Same thing if we want to do, we can do it over here as well. Okay, we can clip them. Means what? Clip them is like replacing these values which are extended to the upper limit. Done. So that's what we identified, but we'll not do anything right now. Okay, we'll just do the analysis as of now. Okay. So now we have a tenure thing. So in the tenure, we'll try to find out how many unique values are there first of all, because tenure can be categorical or continuous both, and unique. So you have 11 unique values, so it seems to be categorical, right? So we can just do a dot value counts. Okay. Dot value COUN. All right. So you find that tenure mostly in the range of the 215 kind of thing. So we can't say that it is highly biased, because yeah, these are having the lesser count, but they're not having very less count compared to others. Okay, like 0 or 10. Okay, 0 or 10 is having a lesser count. Apart from that, they are very close. Okay, they are very close. So this data is also good to go. Balance df1 balance dot plot dot histogram. Okay, so balance mostly here, zero balance is something which we can say outlier. If I will just handle this zero balance thing, then we will have the normal distribution. All right, only zero balance over here seems to be have the outlier, but here in the box plot we don't see any outlier. So we can use them as it is. Yeah, it is something like these guys. We have to check that whether it is a real value or it is value which is not known. It is zero. So this answer can be given by the domain expert. Okay, but generally there is a possibility of zero balance in the bank account, so we can use them. Now even number of products and other things are there. So let's see. So DF of DF1 DF1 number of products dot plot dot value counts. Okay, and then we can plot it dot plot dot bar. Okay, so it's like mostly 1 or 2 product people are using, 3, 4 are very less, isn't it? Same way, let's say DF1 here we have KIT card. Most of the people are using KIT cards. So that's what information we are getting. Like we are getting like which column is, having the bias data and where we don't have the bias data. So here we don't have the bias data, right? So in case, when we build up the model and we get the biased output, so those biased output because of the columns which are biased, right? So then later on, based upon the domain understanding, we just keep or remove the columns which are biased, okay, or based upon the importance of that feature as well, okay, after model analysis. So that's why, later on when we do model analysis, but before that we should know about the data. Okay, so these all things we are doing so that we can know about the data, how data is distributed. Dot plot dot histogram. Okay, so this is what uniform distribution. So nothing to do over here. Okay, we can't do anything over here. All right. So this is what called univariate analysis that we did. Okay. Next, bivariate analysis. So for the bivariate analysis, I want to perform the analysis between geography and exit. Okay. How geography is affecting exited. So please let me know how can we do it. Okay, this is what I have to do. Next, I have to do over here how gender, okay. Next, I have to do over here exit is tenure, okay, tenure. Next, number of products. Just taking the categorical column because last column is also categorical. So initially we are just trying to analyze categorical and category. Okay, next. Has credit card. Next. Thereafter is active and so this is a bivariate analysis that we have to perform. Okay, so please just try to do this thing. You have to do what? You have to just take two categorical column and use cross tab. That's why I'm giving you this particular thing so that it can be, you always you should not forget this thing ever. Right, DF1, then I can take what? Exit. Right. So when you do it, how two categorical columns are related to each other, we find it out, right? And based on it, we can do what? We can do our analysis. Dot plot dot bar. So we can find that in the France we have the exits almost close to Germany, but in Germany we have lesser continuation. Okay, in the Germany we have lesser continuation. In France we have more continuation. Okay, that means in Germany the exit to non-exit ratio is not good. Okay, or you can say not exit to exit ratio. In the Germany, non-exit to exit ratio is not good, but in France, it is good. Similarly, just try to do for others. So by looking at the number, if things are not clear, we can just plot it. Okay. So this is what we have, right? Male and female. We can say that we have the exit. So male and female is also affecting the exits. Okay. Because the ratio between exit and non-exit for female is lesser compared to male, right? Thereafter, we can take it over here for the tenure. Okay, So tenure we can say is not affecting much, right? Only we can say that when the tenure is 10, then only it is there. But number of counts in the 10 is very less. But apart from that, the ratio is almost same. It is not having a major effect. Number of products, we have 1, 2, 3, 4, 0, 1, 2, 3, I guess product. Okay, and you can check it. So number of products, if it is 3, the chances of exit is higher. 4, it is higher. Number of product 1 or 2, the chances of exit is lesser. So this is also affecting. Has credit card. Let's check. So has credit card is having almost the similar ratio. Okay, we have lesser people who are having credit card. So we have more people having the credit card. So that's why exit is also more. Here we have lesser people who is not having credit card. So that's why exit is also less. So this is not having any major effect. Okay. So next we have what? Is active. So we are just doing few analysis to understand our data. Okay, so it's very clear that if someone is an active member, the exit is lesser. But if someone is not an active member, the exit is higher. Okay, so obviously active member things will influence the exit. So this is a bivariate analysis. Bivariate analysis between two categorical columns. Now categorical and continuous column, what should we do? Let's say I have to find out the credit score versus exited. Okay, how these two things are affecting, how exit are getting affected by credit score, right? Thereafter how age, thereafter how balance, and how estimated salary, right? So here we can do what? Balance, credit score, balance, and thereafter age also. Let's say it is age, balance, okay. So what should we do over here? Do you think, like we did cross type for two categorical, but if it is two continuous, then what should we do?
Correlation.
No. Correlation is between two continuous, right? But here we have one categorical and one continuous. Correlation, you said it right. Like for example, if I have to find out the relation between age and balance, it is a correlation. Okay, or balance and estimated salary, correlation. Credit score and age, correlation. But here we have one categorical, one continuous. If we have one categorical and one continuous, then it should be, and then we can do the aggregation. Aggregation, let's say mean. Okay, so it's almost same, right? Credit score is almost same for both the things, like exit and non-exit. Age, age is having some differences. We can say that higher age groups are having more exits compared to lower age groups. Then balance, okay, so balance, so is having a higher average balance and having a more exit compared to lower average balance. This is little opposite kind of thing. Thereafter you have a estimated salary. Okay, so obviously higher estimated salary is showing a higher exits compared to lower estimated salary average. Alright, so it is showing a little opposite behavior than expected. All right. Next, what we should do? Okay. So now we did some sort of analysis. Based on those analysis, we'll take the steps. But first, we build the base model. Right. So in the base model, we need all the numerical value, or if these are the categorical value, for example. Okay, so we have two categorical values. So those are objects. So we just convert them into categorical. So df1, what was that? Geography dot as type category. Okay, so converting this column into the category. Okay, so either you should convert into numerical form using map, or this also we can do. Sorry. One more column is there, which is your gender, I guess. All right. So this is your df1.head. Now we have x is equals to df1.drop. Okay. What columns is equals to exited? Again, y will be equals to what? Exited. Done. Now we do what? You have to split. Thereafter, build model. Thereafter, evaluate model performance. Okay, this is what you have to do. See, it's just a 3-step process. Split from sklearn dot model selection, import, train, test, split, right? Xtrain. Okay, Xtest, Ytrain, and Ytest. All right. So with this thing, the X will be divided into 2 parts and Y also will be divided into 2 parts. Then we build up the model. So for building up the model, we can use from sklearn dot linear model. So sklearn dot neighbors, import k neighbors classifier. So model A is equals to k neighbors classifier. Xtrain and Ytrain. So if you just fit the data into this model, right? So model A dot fit Xtrain, Y. To just find out the accuracy. Okay. But here we are getting an error. It is saying that this value is not a numerical value. So what should we do over there? Please tell me. Here I have to convert it into numerical form. So what should we do there? Yeah. Almost done. You have to just fix this problem. That is the non-numerical data column. You have to convert to numerical form.
So can we create a function to replace each values for geography, all the unique values? Like France can be 1. Spain can be 2 and 3 can be Germany, like that.
Right. That is called data encoding. There are two kinds of data encoding that I told you. One is your label encoding, and other is your one-hot encoding. Right. So where should we do label encoding and where one-hot encoding? Can you tell me? What is label encoding? The example you had given, like France can be 1 and this can be 2. That is your what? Label encoding. Okay. And what is one-hot encoding? Mhm. Okay, I'll tell you. I already told you, but you may missed it. That's why the purpose of saying this example is what, so that you can recall everything. See, whenever we have a categorical data, we have two kinds of encoding option, right? One is called label encoding, and other is called one-hot encoding, right? So when do we perform label encoding? Like you told, okay, like we have a gender over here, like male, okay, or female, right? So here, we can do the label encoding kind of thing, like we can give it value 0, okay, and we can just give it value 1 like that. Okay, as you said, right? Now, label encoding is done for the data where we have just two categories. Okay, like here we have just two categories, so here we can do it, right? Or where we have, kind of a ordinal data, right? So label encoding is possible, or we should do it where we have only two category. Okay, if I have only two category, or it is a ordinal data. Ordinal, right? What is ordinal? That means something you can put into order, like small, medium, large. Okay, this is what ordinal data. So we can just, as it is already ordinal, it is already in order, I can give it 0, right? I can give it what, 1, okay, and I can give it what, 2. Okay, since it is already a ordinal data, it is already in a particular order. So after encoding also, we are not disturbing the order. Okay, we are keeping the order as it is, right? We are not just changing the order. We are just keeping the order as it is. Isn't it? 0, 1, 2. The data is also ordinal data. Okay, so that's how we do it. But if the data is nominal, okay, like we have a France, Spain, and Germany. Okay, what if I have a nominal data? Okay, nominal means what? Something which is not ordered. Okay, which we can't put into a particular order. Okay, like we have over here France. Okay, thereafter we have what? Spain. Sorry, it is nominal. France, Spain, and Germany. So you can't put it into order. There is no way that you can say that, okay, France should be first, Spain should be second, Germany should be third. Okay, there is no order over here. So in such case, giving it an ordinal encoding may influence the the information within the data, or you can say the story behind the data. Okay, since it is not ordered, but you are giving it an ordered encoding. Okay, if it is already ordered, then it's fine. But as it is not ordered, and you are giving it a ordinal encoding, that means let's say you're saying it 0, 1, that means you are putting it into order. Okay, so that will affect the meaning of your data. That's why here what we perform, here we perform the one-hot encoding like France, Spain, and Germany. Okay, so we can do it like this. Then it happens in alphabetical way. So this will be called as 1, 0, and 0. Right. So this will be called as what? 0, 1, 0. Okay. And this will be called as what? 0, 0, and 1. This kind of encoding is called what? One-hot encoding. Right. So generally, if you suppose number of categories are very huge, right? Like suppose you have 10 categories, 20 categories, right? So in such case, giving it the labels like 0, 1, 2, 3, 4 is not good. Okay, if you are giving it 0, 1, 2, 3, 4, what happens? You are forcefully increasing the weightage of some category which had been given a value 10. Because if you just encode it like this 0, 1, 2, 3, 4 kind of thing, then what happens? At some point of time, you are just kind of increasing the category which gets the value 10 or 9 or 8. Okay, some category will definitely get a value 8, 9, 10. So those are getting actually higher weightage. These are getting higher weightage compared to these guys. Okay, so it's like forcefully we are giving them the higher weightage. So that promotes what? That just promotes the biasing in the data, right? So that's why here in this thing, that is your geographical region, we will perform over here one-hot encoding, and in the gender label encoding. Okay. So df1 gender dot map. Okay. Can just map it. It's a male, or it should be alphabetical, or it should be good like female. Okay, and thereafter male. Okay, like that. Okay, so it is a dictionary. If you say defined, if you see over a defined dictionary, so dictionary female can be key, and the mapping value can be this one. Okay, so now we can update this gender column over here like this, right? And then we have to do it for the geography, right? So for so here it is a label encoding for gender. Okay, and then we will perform the one-hot encoding for geography. That is very simple. pd dot get underscore dummies. Okay, df1. So when I do it, automatically it will detect the categorical column. Okay, and make it one-hot encoding. But gender column was also categorical. So it is again doing the one-hot encoding for this guy as well. But I don't want to do it, right? So here we will just pass over here. Columns is equals to geography. That's right. Actually, what we did earlier, we set gender column as a categorical column. So even after encoding, we did here. Here we did the encoding. It's not like that we didn't. We already did the encoding. But still, what happened when we use get dummies picks all the categorical column. So it picks gender as well as geography. But I just want geography. Now I can also use over data type is equals to integer. So if you see over here, 3 columns are created. First sample was from the France, that's why 100. Second sample was Spain, so 001. Third was again France. So wherever it is like that, it just made it, right? So I can just store this thing into df2. Okay, here I can take df2. Here I can take df. So XY is done. Training is also done. Now you have to just evaluate the performance. So can you just let me know what function shall I use to evaluate the performance? How can we calculate the accuracy? See, for calculating the model accuracy, the simple function is score, right? So print model accuracy on training data. It is model A dot score X train comma Y train. Alright, and thereafter model accuracy on the test data X test and Y test. Okay, getting some error. So comma is missing. See a comma outside. So it is close to 81 to 75%. Okay. Now since it is a KNN and you know all the values are of different range, it would be good if we can scale it. So for scaling, I told you the min max scaler, right? So from scale on dot preprocessing import min max scaler, right? So with the scaling, what happened? All the values will be scaled down in the range of 0 to 1. So scalar is equals to what? Min max scalar. So scalar dot fit x, and thereafter scalar dot transform x. Okay, so it will scale down all the values in the range of 0 to 1. So let's use x scaled over here. So we have x scaled. So my accuracy become 80 to 86% as of now. Had I told you about the confusion matrix? Have I ever told you about the confusion matrix? Let me check. No, I have not told you. No problem. First, do up to here. There are so many things that you need to recall. Okay. I'll tell you about the confusion matrix in the next class and the classification report and all. Because here the data is, if you see, here if you check the data initially only, okay, like I have to predict the exit, right? So I will also check over here exit value counts that I have not checked. You can say I did everything, but I have not checked the exit value counts. Okay, that I should check, right? So here, if I check it, let's say over here, DF1 exited with dot value counts. Okay, so here it's a clear a biased data, and this is very important thing to understand. Okay, in most of the interview, people do ask, how do you handle the biased data? Okay. Okay. People do ask, how do you handle the bias? Because here you can say more than 80% time we have category 0. That means it is very clear that model can't predict the category 1 with high accuracy. This is a good model, having 80% accuracy, 82% accuracy. That's good. That's not a bad number. But the problem is we are working on a biased data. And because of biased data, this model may not be able to predict exit with high accuracy. It will predict non-exit with high accuracy. Okay, this model will predict the non-exit with high accuracy compared to exit. So how to identify that problem and how to fix that problem, how to handle the biasness? There are multiple ways of handling the biasness. Like we do the oversampling, undersampling, class weight management. So all those things I'll cover in the next class. Okay, so in the next class, we'll try to understand handling and working with biased data. Okay, I'm not covering today because many of the people have not returned from the break. Again, this is a very important topic that everyone should be there in the class, right? So please go through the thing that we covered till date and do attend the next class so that you can understand this concept properly. And then, when most of probably in the next 2 class we'll finish this one as well as some algorithms as well. Like 3 more classes, I guess we can easily finish our machine learning topic. Okay, and we'll move to the next thing, that is our deployment part. Okay, the model deployment and other things, right? Okay, so that is it for the day. If it is good, let me know. Shall we close it for the day?
Yes, sir. Sir, Power BI and SQL we will starting after that, right?
After this we'll start the Power BI and SQL. Your health is good? I got like you're not good today.
Yes, fine, sir. I've
Fine.
taken medicine.
Alright, yeah. After finishing it, we'll start the Power BI and SQL. Right.
Okay, sir. That's good.
Okay. Thank you.
Thank you, sir.
More specifically, I had given this assignment and you were only doing it. I was just guiding it. So this was a churn modeling thing, right? In which the data that we use, in which we have a output column representing churn yes or churn. Churn means what? Like using a service or not using a service, exit or non-exit. It's churn, right? So this information, using it, we have to build a model which can predict the churn, right? So here, first of all, we remove the columns which are not required for the churn. Like if someone will take exit or will not take exit, that doesn't depends upon kind of some of the information such as row number, customer ID, and surname. Right. So we just remove those columns. Right. So now we are using these values over here. Okay. So with these things, we continue identified that known missing values, did some sort of EDA plot and all. Okay, just identified this univariate analysis. Okay, thereafter we perform some sort of bivariate analysis also. Okay, identified some outliers also in the age column. Okay, and this is a balanced data distribution. Number of products has a credit card, so most of the people are having the credit cards, right? That means the data is slightly biased towards the credit card users. Okay. Now we have other factors also identified. Then we just went through the bivariate analysis to understand how churn is affected by the geographical location. So we identified the exit to non-exit. Like here, blue color is non-exit and orange color is exit. So exit to non-exit ratio in France is good compared to Germany, because in the Germany the exits are almost close to France, right? But non-exits are lesser. That means here some location is actually affecting the exits. Maybe Germany, more people are taking exits. Okay, gender-wise exits, we find that for the female we have more exits compared to male, right? Even the count is lesser. Okay, so these all things we identified, and thereafter these are the like if someone is using the credit card, they are having their more exits, but more people are also using the credit card, so that's why more exit may be there. So this credit card is not so much kind of creating an influence. It's like less people are using credit card, so less exit. More people are using credit card, more exit. So here the ratio is affected by the count only. So these are the understanding we get. Okay, thereafter we are kind of identifying the average estimated salary of exit and non-exits, average balance of exit and non-exits, age of exit. So this is banking data. So like whether the bank customer will keep using the banking service or leave the banking service. So it is representing that one. So average age of exits are higher compared to non-exits. This is what we got. And then we have this thing that is your else type category. Okay, so we converted these two things into the category column. Later on we will encoding it male female into 0 1. Okay, and geography as a one hot encoding. Okay, and thereafter we scaled it, and thereafter we build the model using KNN, and then we identifying the accuracy over here. So up to here we did. So I hope up to here there is no doubts. Okay, and it will clear for you. So let me share the file with you. If you had not joined the last class, you can easily understand. All right. From here we'll go ahead, and also let me check what are the things that has been covered for you. Okay, so just a minute. Okay, so I covered for you regression things, R squared, non-linear regression and others, and classification also I had covered you for this KNN and all. Okay, fine. All right. So today I'll also cover for you the logistic regression most. The logistic regression I have not covered, right? Okay. No, I have not covered. That's fine. All right. So to build up this model, we got the accuracy close to this thing, that is your almost 80%. So the point over here is, if the accuracy is 80%, 90%, can we trust this accuracy or not? Right. So only the accuracy. I'll tell you why. Like for example, if you remember, something I told you initially when I was telling you the regression thing. In the regression, we identified the mean absolute error, mean square error, right? So whether we were only trusting mean absolute or mean square error, or we were doing something else as well. Obviously, we were finding the R squared value. Okay, only mean absolute error, mean squared error is not enough to trust the model. Okay, we identified R squared value. If R squared value is negative, it means it's a bad model. And if it is positive and close to 1, it is good model, right? Same way when you work upon this particular thing which is called classification. The only accuracy is not good to go. We can't just depend on the accuracy. Why? I'll give you the reason first, then I'll tell you what we have to do. Let's say I have the real value in the data given as like this: 0, 0, 0, 1, 1, or you can say let's say 0, then 0, then 0. Okay, like I have the actual level. Now let's say I have the predicted level, right? So predicted level let be YP, right? That means model had predicted this. So after getting trained, okay, so let's say model had predicted this after getting trained at 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Now the point over here is, if you see this thing, if you calculate the overall accuracy, so out of 10 times, 8 times it is correct, right? So overall accuracy is what? 8 upon 10, right? That is 80%, right? But the problem over here in this case, okay, none of the category 1 is correct. Okay, we have two samples representing category 1 and both are predicted incorrect. Okay, that means it is not a good model. For category 0, 100% accurate, and for category 1, 0% accurate. Okay, none of them are identified correctly. Right, it's a totally a biased model. Right. So the point is, how do you identify the biasness of the model? Right. So to identify the biasness of the model, we will work upon over here two things from sklearn dot what matrix import confusion matrix. Okay, and one more thing that is called classification report. Okay, these two things we'll work upon, right? So let's say if I'll just execute it. Okay, so let's say first I will do what I will just make a prediction on the given data, right? So y train predicted value. This is your predicted value on the data used in training. Okay, so predicted values on data used for training, right? So the data that is used for training, so for that let's say the predicted value is model a dot predict x train, right? And let's say the data used for test purpose, so y test predicted is equals to what? Model a dot predict x test. So data we use for the training and some data we didn't use for the training, but we're making prediction on both of them. Now we take the confusion matrix over here. All right. And we will feed both the things like y train and y train predicted. Okay. And then we will also take the confusion matrix for the test data. I'll explain this matrix, don't worry. First of all, let me just get it. Okay, now I'll do what? I'll call over here the classification report as well. That means same thing. I'll copy and paste. Okay, and call the classification report. Am I audible to you properly?
Yes, sir.
What is happening in this thing? Let me use offline. It's creating some issue. Arrange Jupyter notebook. Maybe this is collab may have some issue. Connecting, disconnecting is going on. I'll use Jupyter Colab, so I can use it more smoothly. Hmm. Just allow me for a minute. I'll network. I can't access the data. No, it is accessible. Let me just download it. Yeah, fine. All right. All right. Now I'll do the classification report for the test data as well. In the confusion matrix, we have 4 values, right? So here we have a square matrix in which we have 4 values. All right. So in this 4 values, it's like we have over here the information, you can say like this: real, here we'll call it a real 0. That means this one is representing real 0. Okay. And then this one is representing real 1. What is real 0 and real 1? It's like the number of samples representing the target 0 and the number of sample representing the target 1. Okay, the number of sample that actually representing target 0 and the number of sample that actually representing target 1. All right, in the given data, because in the data you have labels given as 0 or 1. In the data you have one thing that is already given as 0 or 1. Right. So what it represents, number of samples that is representing target 0, that is 5791 plus 174. These many we have samples representing 0 and these many samples are representing 1. Is this clear? Right. Now we have predicted 0 and predicted 1. Okay. So it is like number of samples that is predicted as 0 and the number of sample that is predicted as 1. Right. That means if I write it over here, 5791. That means these many samples are actually predicted 0 and they were also 0 in the data. That means these are correct number of predictions. Am I clear?
Yes, sir.
Okay. And this is again the correct number of predictions. That means 677 times when the prediction is 1, the real label was also 1. Okay. And how many incorrect number of predictions? These are incorrect number of predictions. Okay. Like we have 174 times the prediction was 1. Okay. And the actual label was 0. Right. And we have 858 times the prediction was 0 and actual level was 1. So is this matrix clear or not? Is it clear for everyone? Karthik, for you, is it clear?
Yes, sir.
All right. So this matrix helps us to identify the biasness of the model. Biasness means what? You can just identify how your model is performing for each category. Like for category 0, it is how much accurate? 5791 upon 5791 plus 174. That would be equals to 97%. Okay. And for category 1, how much accurate? 677 upon 858 plus 677. That is 44% accurate. Okay. So this shows the biasness of your model. That means your model is what? Biased. Understood? Am I clear?
Yes, sir.
Okay. Now, similar story you have if you talk about the test data analysis. Let's do the similar analysis on the test data. So for the test data, if I'll do the analysis over here, I get the similar kind of performance matrix. Here, here again I draw it. You should keep responding, right? So that in case if correction breaks down or I just break from my correction loose, so I'll come to know. So now let's talk about this test data thing. Okay, so for the test data we have predicted 0, predicted 1, real 0 and real 1. Okay, so how many times we have correct predictions? We have correct predictions for 1906 times. Okay, we have a correct predictions over here that is equals to 1906 times. All right. Okay, and then we have the next number of correct predictions are 160 times. Okay, so and incorrect predictions are what? 92 and 342. If you calculate it, the accuracy for category 0, 1906 upon 1906 plus 92. This is total number of category 0. This is a correct number of category 0 predictions. So this will come out to be 95%. Okay. And for this guy, it is 160 upon 160 plus 342. That is what? 32%. That is also biased. Obviously, if the train model is biased, on the test also it is biased. Okay. So what is the reason of biasness? The reason of biasness is present in the data itself. If you check the data distribution over here, okay, this data distribution says that 80% sample is category 0 and 20% sample is category 1. So it is very clear that our data itself is biased. That's why at the end model is also biased. All right. So my model is good in identifying the non-churns, but it is not good in identifying the churn. Right. That means when it comes to identify the non-churns, it is identifying it correctly. But when it comes to identifying the churn, that is category 0, the accuracy is very poor. It is just 30% or 40% kind of thing. So this is not a useful model. Why it is not a useful model? Because the true positive rate of this model is very poor. Now, what is true positive rate? Let's try to understand. See, here, this is your matrix. I'll create two matrices over here. Okay. Now, let it be one matrix only. Why two matrix? Let it be one matrix. Better we can understand. Okay. So now we have over here predicted 0, predicted 1, real 0 and real 1. So 0 will consider as a negative class. This one we consider as a positive class. Right. Now, wherever the predictions are correct, we write over there true. And wherever the predictions are incorrect, we just write over there what? False. This is false. Okay. Wherever the predictions are correct, we just make it positive. Okay. So true, positive. Wherever the predictions are 1. Okay. If the predictions are 1, we call it positive. And where the predictions are 0, we call it negative. Right. So true represents what? True represents correct predictions, false represents incorrect predictions. Right. Positive may represents class 1 prediction and negative represents class 0 predictions. Clear? So what is a true negative value over here? The true negative value over here is very clear. It's 1906. And true positive value is 160. Right. Then what is false positive value? 92. And false negative 342. For a model like this, where you have to predict churn. Churn means what? The exit of the customer. Or for a model that you are using in the healthcare, like diabetes predictions. Or for a model that you are using in a financial sectors, like loan fraud, like credit card fraud, loan approval, credit card approval. So in those cases, the true positive matters a lot. Okay, true positive, because in this case, what we want? We always want that the person who will leave the service, I should know about him, so that I can, influence him to not leave the service. Okay, like it's a banking data, so I don't want that customers should close their bank account. Okay, so if I don't want customers to close their bank account, so what I want to know that when the customer is leaving the service, right? So this value matters a lot. Overall accuracy, compared to overall accuracy, true positive value matters a lot. But here true positive itself is very poor. So this represents that model is not good even it is having 80% accuracy. This is not a good model, right? And then we also find out something which is called true positive rate, right? So what is true positive rate? This will be equals to true positive upon true positive plus false negative. So can you tell me what is a true positive rate over here? What is a true positive rate? It is 160 upon 160 plus 342. That would be equals to 0.32. That is true positive rate. Am I clear?
Yes, sir.
Okay. And what is true negative rate? True negative. That means this will be equals to true negative upon true negative plus false positive. That will be equals to 0.95. Right. So this value is true positive. This value is true negative. Correct. So the true positive rate and true negative rate shows it's a biased model. Second, what is precision? Precision is calculated vertically. See, true positive rate, true negative rate calculated horizontally, or recall value is calculated horizontally. Recall value you calculate like this. Out of all existing positive class and out of all existing negative class. Again repeating, out of all existing positive class and out of all existing negative class. The correct number of positive predictions and the correct number of negative predictions. Again, that is true positive rate and true negative rate. Right. And out of all positive or negative predictions, out of all positive or negative predictions like this. Okay. Out of all positive, so out of all positive negative predictions, 1906 plus 342, the correct number of predictions, 1906. This is what? Precision. Out of all positive predictions, what is total positive predictions? 92 plus 160. Correct prediction is 160. This is what? precision. Precision for 0, precision for 1. When you combine precision and recall together, we get F1 score. 2 into precision into recall upon precision plus recall. Right. So these all metrics when combined together, it gives you the performance matrix. You can see the F1 score formula. Right. So when these all metrics combines together, it tells you that whether your model is biased or not. So it clearly shows that your model is biased. Okay, all the values are quite wide. They are having a good sort of differences. Right. So this kind of model is not accepted where you have a biased nature. And why it is biased? It is biased because of data is just the data that we have that is actually biased data. So the data is biased, obviously at the end model will also be biased. Understood?
Yes, sir.
Okay. Sure. Karthik message, but it is not informed to me actually. Karthik, you can directly call me, like in case if you have my number, in case connection breaks and it's more than 5 minutes, I don't come back. Just give me a call. It means I have not noticed.
Sure, sir.
Okay. Right. Okay. So next thing. So this is done. So now how to control this biasness? So to control this biasness, we have the undersampling and oversampling technique. Undersampling will do what? See. I have to increase the true positive rate at any cost. Okay. The true positive rate should be high. That is the thing, because I have to predict the churn. Right. So in many cases, compared to accuracy, the true positivity is very important. Whenever you build any predictive model, your stakeholder will ask that what is your true positive rate, right? So you should know what is true positive rate, right? So undersampling will do what? Will just reduce the sample size of majority class. Okay. The majority class sample size will reduce. It will become 2000. Right. So by reducing the sample size, right? So what you can do from IMB learn dot undersampling. IMB learn is imbalance learning. Import random undersampler. So RUS is equals to thereafter you can do what? Just use RUS dot fit resample x comma y xu yu. So this will reduce the sample size from the majority class. Okay, if you see yu dot value counts, it reduces the sample size from the majority class, right? Okay. So next what we do? The same thing that we did, we have to scale it, split it. This is for scaling. So just scale it. Okay, then this is for splitting. Split it. Okay. Thereafter, for the training, okay, and thereafter we'll calculate the accuracy. Okay, so here instead of x, we will use what? XU. Okay, and here we split X scaled, that is a scaled value, and Y hue, the target column. Right. So now if I split and then this is a score, so it comes out to be a underfit kind of situation where the accuracy draw down. Okay, initially it was 95%, it came down to 79. Initially it was 80% something, right? 86%. So from here it came down to 79, as well as this accuracy is something which is also came down. We'll try to identify its biasness. So for the biasness, we'll call classification report. Okay, and in the classification report, we'll just feed over here Y train. Okay, and then model. Here I should use model B actually. The model A was. Alright. So here model B dot predict what? Your X train, right? Okay. So you can say biasness is somewhat handled. This accuracy was 45%, but now it is 77% on the train data. And on the test data, let's say, also it improved. It becomes 66%. But the overall accuracy came down. Right? Why overall accuracy came down? Can anyone tell me? Because we have reduced the data. Right? We just removed more than 50% of the data. Okay, from category 0 only we removed, but we removed more than 50% of the sample, right? That's why the model accuracy will be affected. Biasness is handled up to some extent. It is not that much biased, but still overall accuracy came down. Okay, so this is what we did over here, that is undersampling. In the undersampling, we reduce the sample size from the category 0. Am I clear? Please tell me, any doubts over here?
So it's a little confusing actually.
What is confusing? Let me know. I'll explain.
So actually, one thing I want to know, like, how do we say ki we need to use the confusion matrix? I mean, I understand that there is a biasness, but then like, suppose there is some other data sample, how will we identify that we require to use confusion matrix?
Some other data sample I didn't get, like, see, whenever you have the categorical data, that means if you are working on any classification model, right? So always after calculating the accuracy, you have to check the confusion matrix, isn't it? Like, you know, because overall accuracy came out to be what? Overall accuracy coming out to be 86-82%, right? So that 86-82% can be this kind of situation also. Let's say this is your actual label having the values given like this, and the predicted are all 0. So here also accuracy is what? 80%, right? But this 80% is not meaningful because 2 samples are there for category 1, and for both the sample it is inaccurate, isn't it? So
Yes.
whenever you build any model, like here is a classification model that we build using K-Neighbors classifier. Understood? Now after this, we identified the overall accuracy. Right. Now we want to understand how is it performing for each category. I have 2 categories. One is churn, other is not churn. So how is it behaving for each category? So that information you can get through the confusion matrix. Right. So with the confusion matrix, we understand that, yeah, this is a biased model. Right. This helps you to understand that, okay, this is a biased model actually. And if it is a biased model, then we try to find out the region of biasness. The region of biasness is most of the case is what? The data distribution. Okay. Here we have 80% samples representing non-churn. That's why for the non-churn accuracy is 95%. Okay, and we have only 20% data representing churn. That's why only 32% accuracy for the churn. Okay, so this distribution should be close. Okay, it can be 50, 50 40, like one can be 50%, other can, like, one can be 55%, other can be 45% kind of thing. Okay, the difference should not be more than 10%, right? So we use the undersampling, that we reduce the sample size from here, from the majority class, remove some samples, so that both can be of equal in sample. It's very simple, like, if any one of your, if the data you are using is having one of the categories in majority, obviously machine will learn about that particular category which is in majority. The majority class will influence the model. You just build up the model, any classification model. At the end, you have to check the confusion matrix. Okay, because confusion matrix will tell you the story about the actual categorical performance. Overall performance is one thing. Okay, this is your overall performance, but you also need to check that if my model is expected to predict category 0 and category 1, so how is it performing on category 0 and how is it performing on category 1? Like here, it is 97% accurate for category 0 and 44% accurate for category 1 on the trained data. But on test data, it is 95% accurate on category 0 and 32% on category 1. Okay, so what's the reason of this biasness? The reason of biasness is biased data distribution. 80% samples are representing category 0 and 20% category 1. Isn't it? So if I can, kind of make this distribution less biased, model performance will also be less biased. So one of the technique of handling the biasness is undersampling. Just remove some sample size from here, right? So that your data can be less biased, right? And at the end, it's like both becomes 2037. Now we are using that particular data for the scaling. We are not using X, we are using XU. XU is a less biased data. Here we have the sample size is same for category 0 and 1. Then we train on it. Then we find the accuracy is little low because we reduce 50% of the sample. But at the end, the biasness is handled, okay, up to some extent. The difference is over here not that big. Okay, only 4% difference we have between the accuracy of category 0 and accuracy of category 1. Okay, yeah, the accuracy is little less, but the difference is also less. Now tell me, what are the confusions over? Just let me know. Yeah, Karthik, please
Sir,
tell me.
So I just want to know one thing, like after we undersampling, like after like removing all the 5,000 rows for the 0 1, like the 0, like how will we say ki the 2001 is, like, suppose after that also we are splitting the data into test and train, wouldn't that be ki, like, the test size can get the most of the zeros or most of the ones from it, like that way?
That is possible. That is possible actually. So when we are splitting this thing, okay, that is a good question actually. You asked. Let me just explain it like this. Okay, so when you split it, right? So there is a possibility that your Y train may get still biased, right? Isn't it?
Yes,
or
sir.
Y test will also get biased. Okay, this guy can also get biased, right? But generally don't happen because you have an equal sample size, but let's consider it will get biased. So for that part, what we can do, we can use one more parameter over here, which is called stratified sampling. Just a minute, there's a parameter called stratified. Let me check is equals to true. No, stratified. stratified sampling. Okay, the parameter I'm missing over here. Just a minute. The parameter just I want to know. Stratified sampling. Scale. Stratify, okay. Just stratify I have to use. You should know the concept, right? So if you forget these parameters, you can find it out. So if I use stratified, right, YU, so it will split and it will keep the same ratio as it is. Now if I split it, it will be 50% in both the sides. Okay. If you think that after splitting, again there can be a biasness. We have 20370 and 2037. So if you put the stratify into this one, then their ratio will remain same. Okay, 50%. Okay, then you can use it. All right. Now is it fine?
Yes.
Yeah, Karthik, you tell me if you have any confusion. You said like you are having some confusion. Karthik, are you there?
Yes, sir.
Is it clear?
Yes, sir.
Okay. So the major drawback of this, this guy that is your undersampling is sometimes model gets underfit. Like here only it gets underfit. Okay, your accuracy comes down drastically. Okay, the accuracy of your model comes down. We don't want the accuracy of the model to come down. Okay, so if we don't want the accuracy of the model to come down, then what we use? Oversampling. All right, because undersampling is reducing the sample size. Okay, undersampling is doing what? It's just reducing approximately, as you said, 5,000 samples from here. Okay, so those 5,000 may have some important information, isn't it? So it just what we need to do, we need to kind of we just don't want to reduce those huge number of sample, because reducing those huge number of sample is doing what? Is making the model underfit, isn't it? So if I don't want to reduce those huge number of samples, what we can do? We can just use over here oversampling. Okay. So again, let's check. Here we have y dot value counts. Okay, so we work on the oversampling over here. So from IMB learn dot oversampling import SMOTE. Okay, and here I will call ROS is equals to SMOTE. What is SMOTE? SMOTE meaning over here synthetic minority oversampling technique estimation. All right, I'll do what? Just use ROS dot fit underscore resample. Okay, X comma Y. So it will give me what? A data in which both the category is having now 7963 sample. That means here nothing is removed from the majority category, rather some data points are added in the minority category. Right. So how it is adding? Is it creating a duplicate? Yes, it can create the duplicate values if you will use over here random oversampler. That means instead of using this thing, if you are using simple, random over sampler. Okay, if you are going to use this thing, then obviously it will create the duplicate values. Okay, random over sampler will do what? Will just create the duplicate values, isn't it? But we don't want it to create any duplicate values, right? Because duplicate values will increase what? Will increase the redundancy in the data. Okay, if I will do it like this, it will create the duplicate values from the minority class, and that will just increase the redundancy in the data. We don't want that. So we are using SMOTE. SMOTE will not create any duplicate value. Then what SMOTE does? SMOTE will make use of this process. Okay. What process it is? Let's say I have a data distributed like this. Where I have two categories. Let's say this is class 1 or class A. This is class A, right? And thereafter we have a class B. Okay. So SMOTE will do what? Will pick any random data point from here, which is in minority class. Okay, it will take a random data point in the minority class and will pick the nearest data point from it. Okay, let's say it took this particular data point in the minority class. Okay, it just took this particular data point in the minority class, and then from here the nearest data point. So nearest one is this one, and then it will generate some new points over here. All right. Then it can just do the same thing over here. Some new data points on this nearest line. Some new data points on this nearest line. Okay. So there will be a random data point. From that random data point from a minority class, next nearest data point will be picked up, and the line, the shortest line connecting them, on that line new data points will be generated. That is called SMOTE. Okay, if you see the definition of it, you'll get it. SMOTE do what? SMOTE first identify the minority class. For each minority class instance, it finds the k nearest neighbors. Okay, from the minority class. Then SMOTE then creates new synthetic sample by randomly selecting the neighbor and interpolating between the two instances. This involves creating new data point along the line segment connecting the original instance and its chosen neighbor. Am I clear? So this process will go again and again until unless it gets the sample size equals to the majority class. This is called SMOTE. Please let me know. Is it clear like what SMOTE does? That means it will just increase the sample in category 0 like this. Am I clear with it?
Yes, sir.
Okay, so it means what? Now what we do, again we can split it like we split it last time. But before splitting, I have to do the scaling. Okay, what I do now, XO I will do for scaling, And for the splitting also, scaled value and YO, right? And stratified will be YO. Okay. Now I can do what? Print y train dot value counts and then y test. You can see equal sample size. Next, we'll build up the model. Model C. So here my accuracy is not coming down, but we have to check whether the biasness is better or not. So again, let's check the classification report. Model C. So here, without affecting the overall accuracy, my biasness is also handled. Now your category 0 and category 1 both are getting predicted with accuracy of close to 90% on the training data, and on the test data also it is, so we can consider it 85% because this data is something we trust more. So 85% of accuracy both for category 0 and category 1. Am I clear? Kenan algorithm, and we had seen how biasness can be handled. Next algorithm that we have to understand is related to logistic regression. Now, logistic regression name maybe it's like regression is there, but it is used for classification. Okay, don't get confused with the name that okay, it is a regression model. No, this is a classification model. All right. So here, it can be used for the classification. How I'll tell you. Let's say I have a data in which two class present, like we had seen churn. Okay, class 0 and class 1. Okay. So now we have some samples which are representing class 0. Okay. And we have few samples which are representing class 1. All right. Now, if I know linear regression, then what linear regression does? Okay. So this is linear regression basically try to identify a best fit line. Okay. That will pass through the data. Right. A linear regression will just try to find out a best fit line which will pass through the data. The nature of this best fit line is what? It is at minimum distance from all the given points. Okay. So what is the equation of this best fit line? Can anyone tell me? This is the equation of best fit line. By using the value of x and y, your linear regression algorithm will try to find out the best suitable value for W0 and W1. Again, I'm telling you, by using the values of x and y, your algorithm will try to find out the best suitable value for W0 and W0 and W1, which can give me the minimum error between y and y hat. Okay, I want this minimum error, so algorithm will try to find out the best suitable value of these coefficients, which are also called trainable parameters or coefficients. Okay, a value of coefficient which can give me the minimum error. That is what algorithm will try to find out. And to find out this thing, which process it uses, can anyone tell me?
So we find the MA.
Which process?
Error.
Yeah.
We actually mean the square of the errors and then partially.
Correct.
So we then.
Correct. That is called gradient descent, right?
Yes.
Okay. By gradient descent process, it will optimize the error, and while optimizing the error, it will find out the best possible coefficient. Again, I'm telling you, by using gradient descent, it will optimize the error, and optimizing the error will give it the best possible coefficients. All right. So that is the whole process that it will follow. Okay. Now, the problem, if I can apply linear regression over here, it will give me what? Output of y can range from negative infinity to positive infinity. The output of y will range from negative infinity to positive infinity. Isn't it? Okay. But what we want? We want the output of y as a 0 or 1. I want my model to predict the output of y as a 0 or 1. Right? I don't want to be kind of in the range of negative infinity to positive, because suppose I build a model and that is predicting, let's say that is predicting 3251 or 3251. So what it means? This is not 1, this is not 0. Or suppose it is predicting minus 256. So what it means? Nothing. Right? So the predicted value is something which is important over here. Okay. It is like, if it is predicting anything from negative infinity to positive infinity, that will not make any sense. Okay. It should predict what? It should predict the outcome as a 0 or 1. Isn't it? It should predict the outcome as a 0 or 1. Right? But using linear regression, it will give me anything between negative infinity to positive infinity. So what we do? If this is my linear equation, I'll modify it like this. Now it can't be negative. Okay? It can't be negative, it will be always positive. Okay? We just use exponential value and it will be what? Always positive now. Alright. That means now it will be like this. From 0 to infinite. Okay. So now this equation will give you the value between 0 to infinite. Okay. So 50% problem is solved. Okay. We build the equation which will give you always positive, but still it is giving me what? From 0 to infinite value. Right. I want it to be between 0 to 1. Okay. So if I want it to be between 0 to 1, what we do? We make the next modification. E y hat upon E y hat plus 1 is equals to E w naught plus w1 x upon. Okay. So now it can't be more than 1 as well, because we added a numerator.
It's e power 0.
Yeah.
Actually, in the denominator, you added plus 1. That indicates it's e power 0. So it's from 0 to 1. Is it like that?
E power 0? Where is e power 0?
No, sir. Like the 1.
Okay. No. It is not like it. It is simple, like, we have some equation over here, right? I want this to give me a value in the range of just 0 to 1. Right. So that's why we just added 1 into the numerator and divided it and put into denominator, like this thing, 5 upon 5 plus 1. It can't be more than 1 at any situation, right? Isn't it? This thing can't be more than 1. It will be always lesser than 1. Isn't it? So it is similar to that. We are just adding 1 into the numerator and putting into the denominator, so that it can't be, the output should not be more than 1. All right. That means this will give you the output always in the range of 0 to 1. That means we get an equation like this, where W0 and W1 is our trainable parameters that model needs to find out for minimum error. Okay, where I can write it like this: C is equals to 1 upon 1 plus. Is it the same equation? These two equations are same, right? Any doubts in it? Are these two equations same?
Yes, sir.
Okay, so it means what? We got a equation. Using this equation, if I will train the model, how can I train the model using this equation? See, I have the given data. Okay. Data is having a feature and label. Okay, so there are some features given. For these features, I have a label given like this. Okay, now what we do, we put this feature value into this equation. Okay, this x value will put, right? So let's say z is equals to 1 upon 1 plus e to the power negative of w0 plus w1 x. Okay, here if you put the value of x for certain value of w0, let's say 1 plus 1 into, suppose x value is 2, right? So you will get the value between 0 to 1. Okay, let's say you are getting a value 0.3, let's say, right? That means here the calculated label is what? 0.3, 0.7, 0.4, 0.5, 0.7, 0.8, 0.6, 0.4, something. Using which I can calculate the error. What is the error over here? Minus 0.3. What is the error over here? Minus 0.7. What is the error? 0.6. What is the error? Minus 0.5, 0.3, 0.2, minus 0.6, 0.6. Okay, so now we calculated the error. Now there is a error optimization algorithm called gradient descent. What that will do? That will tune the values of these coefficients so that these error can be minimized. Okay, so these coefficient value will be tuned just like in the linear regression so that this error value can be minimized. That is the whole target, right? So by the repetitive process, your error value, your coefficient value will be changed. Okay, this will be tuned to minimize the error value over here, and at the end you get a trained coefficient which will give you the minimum error. That means if your model is predicting, okay, after your model get trained, after the training, okay, it will have the coefficients as W0 and W1. Okay, so using which the value of z will be identified as between 0 to 1. So if the value of z is more than 0.5, okay, so prediction will be considered as 1. And if the value of z is lesser than 0.5, the prediction will be considered what? 0. Am I clear?
Yes, sir.
Right. So that is what logistic regression do. Here also the process remains same like linear regression, only the equation is changed. Okay. In linear regression, we use simple linear equation to find out the value of y hat. Okay. In linear regression, what do? You use simple linear equation to find out the value of y hat. Using y hat, you calculate the error, and then you tune the value of w0 and w0 one for minimizing the error. In logistic regression, we make the change in the equation, okay, so that you get the kind of equation which can give you the value in the range of 0. It will not give you anything, so that the error minimization can be easier. Right. So if it will give you the value between 0 to 1 and the final target is just 0 or 1. Okay, final target is only what? 0 or 1 over here. Right. So as the final target is just 0 or 1, then obviously your error optimization will be done easily and you can get the better performance. Okay. So if I have to implement this thing, logistic regression. Okay. So I required X and Y. Okay. Then I'll split scaled and split it. I'll not do any oversampling or undersampling, right? Okay. Then I'll define from sklearn dot linear model import logistic regression, then model log A is equal to then model log A dot fit X train comma Y train. Okay. Then once the model is fit, I have to do what? I have to find out the performance. So I'll just copy and paste the same thing. Model log A so it is 81%. Right. Now I'm giving you this file. Please let me know what is a true positive rate and what is a true negative rate using logistic regression. Just please let me know the true positive rate and true negative rate using logistic regression. Just one line of code is required. See, to identify the true positive rate or true negative rate, okay, that is accuracy for positive class, that is category 1, and accuracy for negative class, that is category 0. You can just call over here classification report from sklearn dot metrics import classification report. Right. And then what to do? What are the two parameters we have to give in classification report?
So the predicted value and the exact value of Y.
Right, correct. Nice. So you can just give over here the predicted value. That means your Y train and the model log dot predict X train. That's it. So it is obviously I have not done any kind of oversampling or undersampling. So it will give me the biased result. Okay. For both the thing, I'm getting the biased result. Now, perform undersampling is not important. Now just evaluate the performance. Okay. Evaluate the model performance after oversampling. Just 2-3 lines of code is required, but I want you to do this thing just to make sure that you have the steps clear. See, for oversampling, what you need to do, you have to just use from IMB learn, right? Import IMB learn.oversampling import SMOTE, right? So that will take care of everything. Okay, so from IMB learn dot oversampling import SMOTE, right? And then we can define ROS is equals to SMOTE, and then just ROS dot fit resample X comma Y. So it will give you the oversample data. And once you have oversample data, you can do what? You can just scale XO XO here YO. All right, and then we can build up the model using this new data. Model log B and the accuracy of the model. Almost 82%. This is better than your KNN. Here the train and test are having a very close performance matrix. Then classification report. Almost 80% we have. Okay, and then test. Okay, so both the side it is close to 80%, right? So here also, if you see in the logistic regression also, we can handle the biases with the help of oversampling. There is one more way of handling this kind of situation. If you have a biased data, that is called handling biasness using class weight management. Okay, this is what I'll explain you. Meanwhile, please let me know if you have any doubts to ask. Just refresh this code and let me know if you have anything which is not clear so that we can cover that and then we go for the next question. Now, what is class weight management? See, when you are building up this thing, okay, in case, there are so many situations where you can't, just a minute, where you can't increase or decrease the sample size. Okay, like suppose you are working on the medical data or any kind of very highly sensitive data, right? So in that case, you can't increase or decrease the sample size. Then in that situation, what you can do? All right. So in such situation, when you are creating this model over here to be trained, okay, here you can give higher weightage to that class which is having a lesser sample size. In the same ratio in which sample size is divided. Like here the ratio is what? 1:4, right? Like it's like, the category 1 is just 20% of total data and category 0 is 80%. So here I can define class weight is equals to category 0. We can give it a value, let's say 1. So category 1, we can give it a value, let's say 4. That means I am saying that make the class weight while training, while you perform the training. So performing the training, you have to more, kind of tune these weights. So tune these weights, but along with that, wherever the category 1 is there, okay, the weight value consider 4 times the weight value of class 0. Okay, so it means what? If suppose weight value is over here, okay, let's say if the weight value is weight 1 is equals to, let's say like this. Weight 0 is equals to, let's say 1. Weight 1 is equals to, let's say 1. Okay, and I'm using W0 plus W1x. Okay, so the value will be what? And let's say x is equals to 2. Right. So 1 plus 1 into 2, that will be equals to what? 3. But if I use weight 0 is equals to 1 and weight 1 is equals to 4, then W0 plus W1x, that would be equals to 1 plus 4 into 2, that would be equals to 9. So how it will be impactful? It will be impactful. I'll show you. See this value. So 0.43 and something. But the target is representing 1. But 0.43 will represent what? 0. So if I use 4 times, then this value will increase and it will cross 0.5. Okay. So, even with a lesser number of category, the weights will be tuned in a way that at the end your model will learn how to predict 1. That is what called class weight management. We give the higher weightage to that categorical class which is in minority, right? Not in class weight. All right. Now see here, I'm not doing any oversampling, no undersampling, nothing, right? Only class weight management. And with the class weight management, let's try to check let it be D over here. Okay, so here it is trying to be 72% of accurate, right? And if I'll try to check the classification report, you can see that for category 1, that is true positive, it increased to 94%. Okay, and this is also becoming 94%. Okay, so here the true positive weight we enhance by enhancing the class weight. One more thing that we should do over here, I have not done, that is called scaling.
Can we use class weight in different algorithms?
We can use. You can use in any algorithm class weight. It is just kind of giving a higher weight to that particular class, which is lesser, right? So here it is X is scaled. After scaling, where I'm doing the splitting, I'm not doing a splitting here. Let me do the splitting also. I guess it is using the fast splitting. This is your X and Y. It is a scaled. Thereafter, it's a splitting. X scaled, scaled, Y. Okay, fine. Splitting. Then train it. then check it, it will be better, then evaluate it. So overall, so now you can see each categorical accuracy is close to the overall accuracy. If you want it to be more accurate for category 1, you can increase this weight, let it be 6. So if you make it 6, it will be more accurate for category 1. Right. So there are many situations when you find that your stakeholder will ask that I want higher true positive rate. Okay. True negative rate is not my concern. Right. So those who are not leaving the service, if they are identified as they are going to leave, it's okay. We can just focus them more. But those who are leaving the service, they should be correctly identified. Okay. Those who will do the fraud with the bank, they should be correctly identified. Those who are not going to do fraud, if they are identified incorrectly, it's okay. No problem. No financial loss. But those who are going to make fraud, they should be correctly identified. The true positive rate is very important. So by managing the class weight, we can do that. And what class weight actually does, you can see over here. Right. So here I was just trying to use something which can give me a value lesser than 0.5, but I'm not getting it. Maybe, some value that is there. So, or we can do what? Let me just try to find out the final coefficient it is having. Print model log A. It's a model log B, right? Model log B is there. So model log, but here we have the so many coefficient. Okay. So these are the coefficients we are getting. Right. So this is also how we can kind of balance the thing. So now these many things you can practice. Okay. In the next session, I will tell you about the support vector machine. Okay. And decision tree classifier as well. Meanwhile, just practice these many things, just go through the things, and what these weights and all represent, that also we'll try to discuss. Just let me know if you have any question to ask from here. So we got at the end, when model get trained, we get the coefficients over here. Now with this coefficient, what information we can gather? What are the information that we can understand from these coefficients values, right? We have to understand it, right? So let's see. I'll just take this coefficients and convert this thing into a data frame. Okay, that is okay. So now this is a data frame. Now you can see we have 11 coefficients. Why do we have 11 coefficients? Because we have total 11 features that we use for the training. All right, these are the 11 features that we had used for the training. Isn't it? That means each coefficient is basically representing one feature importance. Okay, how a feature is important, right? So it's like what we will do, we will just assign, let's see, this is a coefficient we have. Okay, so coefficient dot transpose, directly transpose I'll do over here. Okay, now I'll assign the column name, index over here. Let's say this is a coefficient table. Okay, and this coefficient table index value will be what? Okay, the coefficient table index value will be equals to these columns values, right? Like this. And then we will have the coefficient table over here, which is having the information like for each particular feature we have one single coefficient. Okay? These are those weights values. Right. Now, what we can do to understand how each of the factors are affecting the target, we can use dot plot dot bar. Okay. So we get the information over here that credit score, if credit score is increasing, right? So the chunk is decreasing. That means if we have a higher credit score, the chances of leaving the service is lesser, isn't it? Same way for the gender, how we had given it 0 and 1. So for the male, we know that for male, when we did the EDA, okay, when we perform EDA over here, if you see, what we find that for the male, the chunk is lesser, okay, compared to female. Okay, or like leaving the service or exit is C. Over here, exit, male. This is male and female, right? Now, when male and female we analyzed with chunk, where did we analyze it with the chunk? Here. You can see for the male, the chunk is lesser compared to female, right? So that's why when we analyze the coefficients, you find the same thing. Okay, for 1, it is negative. It is negative means what? When the gender is getting 1, the chunk is decreasing. That means chunk is going towards 0. It's inversely proportional. Age, as the age increasing, the chunk is also increasing, or exit is also increasing. So whatever things that we identified in the EDA, the similar kind of a story, this particular coefficient is also giving us. So we can understand that for which particular information, the probability of chunk is increasing. Like as the tenure increasing, the chunk, or you can say exit, is decreasing. Okay, as the balance increasing, the chances of chunk is also increasing. Number of product increasing, the chunk is decreasing. So it's like kind of which one is directly proportional, which one is inversely proportional, that we can get with the help of coefficient analysis. All right, now let's try to work on the next kind of algorithm, that is called decision tree classifier, right? So I'll explain that first. Okay, so what are we going to do? We will understand over here the decision tree classifier, right? So decision tree classifier basically works like this. It forms the tree. Using the given set of information, it will just form the tree to make a decision. Okay, using the given set of information, it will form this kind of tree, and this tree will help us in making the decisions, or help the algorithm to make the decisions. So this is again we can use for classification purpose. Very simple to use. I'll tell you how this kind of tree will be formed. Okay, now the point is how this tree will get formed and how it will make the decisions, right? So let's try to understand it. Okay, so to understand this thing, let's have a data. I'll define a dummy data over here, right? So let's say this is a data containing few informations such as temperature value, okay, and let's say temperature, and let's say wind speed, okay, and here is a game, okay, like some game, like it can be a golf or something like that, right? So I have some information given, like temperature value 31, wind speed is let's say 40, okay, 27, wind speed is let's say 30, 28, let's say wind speed is 35, 25, wind speed is let's say 55, 27, wind speed is let's say 22, okay, 35, wind speed is let's say 29, okay, 36, wind speed is let's say 45. Okay, 32 in this case, let's say 40. Now we have the output. So output is like, let's say here the game was played, here game was played, here not played, here played, here not played, not played, played, not played. So randomly I have given it, right? So I want to do what? I have to predict for a particular situation. That means this is data given to us, right? Now I need some kind of a process which can predict the outcome in a certain situation. Okay, certain situation is like, let's say there is a value over here 30, wind speed is 42. So whether it will be yes or no. Okay, I have to predict it. Right. So what I can do? First of all, I'll go to root node. In the root node, all of them will be assembled. Okay, we have yes, yes, no, yes. Okay, yes, yes, no, yes, then no, no, yes, no, 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 yes, no. All of them will be there. This is what root node. Okay, once they will be there, we have to calculate over here a value called Gini index. What is Gini index? Gini index also you can say it's a impurity index or the matrix to calculate impurity of a node. What is this matrix? This is a matrix which can calculate the impurity of the node. Right? So what is the formula of it? 1 minus sum of probability of each category and the square of it. Okay, to calculate the square of each probability and sum it up. That means this is equal to 1 minus, what is the probability of yes? 1, 2, 3, 4. 4 upon 8, that is 1 by 2 square. That is 1 by 2 is 0.5. So it is 0.5 square. Let me write it over here. Probability of 1 square plus probability of 0 square. That is equal to 1 minus 0.5 square plus 0.5 square. That is equal to 1 minus 0.25 plus 0.25. That is equal to 1 minus 0.5, that is 0.5. This is the initial Gini index. Okay, this is a Gini index of what? The first node or root node. Right. Now, how this Gini index can help you in forming the tree and making the decision. Okay, this Gini index will help you to form the tree and make the decision. That's what is called decision tree classifier. So now what happened, based upon certain criteria, okay, like temperature or wind speed, anything you can take. Okay, let's say temperature I am taking. So minimum value of temperature is 27, right? And maximum is what? 36, right? So here I can tune it like this. Temperature value lesser than what? Lesser than 27, lesser than 28, 29, 30, 31, 32, 33. This is how it can be tuned, right? So step by step we have to tune, but let's say I'm just putting out 27, 28. What is the middle value between 27 and 36? 27 and 27, 6, 7, 8. Okay, so 27, 28, 28, 30, let's say 31. Okay, let's say 31. True and false. Okay, now what happened? Whenever it is lesser than 31, where it is lesser than 31? Here, 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 here. Okay, these 4 it is lesser than 31. Right. So I can say what? Here, 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 right? Yes, no, yes, no. Right. Here I am having yes, no, yes, no. So again my Gini index will be 0.5. Okay. Let it be lesser than 32. Okay, so this will also come. Right. So let's say over here I have the value 31, 40, yes. Then again we have a yes. This one, this one, this one, this one, and this one most probably, right? Yeah. So it is yes, Okay. It is what? Yes, then again yes, then no, then again yes, then no. All right. Temperature value lesser than 32. Okay, and then no, yes, no. Okay, now you have to calculate the Gini index for these guys again. That means you have already calculated the Gini index for the root node. This is the Gini index for what? For the root node that you have already calculated. All right. Gini index of root node is already calculated. Now you have to calculate the Gini index for these subnodes, right? So for, let's say, calculate it over here. 1 minus 3 upon 5 square plus 2 upon 5 square. That would be equals to 1 minus, what is 3 upon 5?
0.6.
Right. So 0.6 will multiply by 0.6, that is 0.36. Plus 2 upon 5 is 0.4 multiplied by 0.4. That is 1.16. That would be equals to 1 minus. So 0.48 most probably.
0.52.
Yeah, the output, the final output is 0.48, right? Just a minute. Okay, and for here it will be what? 1 minus 1 by 3 square plus 2 by 3 square. That would be equals to 1 minus 1 by 3 is 0.33. 0.33 multiplied by 0.33 is 0.11 plus 2 upon 3 0.66, so 0.66 0.44. The 0.44 plus 0.11 0.55, that is 0.45. Okay, so you can see when one of the node, when in any node one of the category is getting in majority, like in this yes is getting in majority, in this no is getting in majority. When any category is getting in majority, what happens? It's like the Gini index reduces. So Gini index keep reducing if the if one of the category will be in majority. If both of them are equal, having the equal weightage, Gini index will be 0.5. But if any category is in majority, Gini index will reduce. Right? It means we have to reduce the Gini index. Okay, we have to use, or algorithm will use this parameter in such a way that Gini index should keep reducing. Right, now how it will find out whether the Gini index is reducing or not? By using information gain. What information gain? What is information gain? Information gain is the Gini index before division. Before division Gini index, that is Gini index 1 minus the weighted sum of Gini index at the next stage. Okay, Gini index 1 minus weighted sum of Gini index 2. What I mean? Gini index 1 is 0.5 minus what is weighted sum? Weighted sum is over here 1 to 5. I have 5 samples. Total sample is 8. 5 upon 8 multiplied by 0.48. Okay, plus 5.8 multiplied by 0.48 plus 3 upon 8 multiplied by 0.45. Okay, so this will be equals to 0.5 minus 5 upon 8, 5 multiplied by 0.48, that is 0.3, plus 3 upon 8, 0.375, multiplied by 0.45, that is 0.17. That is equal to 0.5 minus 0.47. That is equal to 0.3, right? Isn't it? So here the information gain is positive. Okay. If the information gain is positive, that means this particular division is acceptable. Okay. If the information gain is positive, that means this particular division is acceptable. If it is negative, that means that particular information, that particular division is not acceptable. Like for example, if you use 31 over here, because of 31 information gain will not be positive, right? So it will always try to use a parameter which can divide the data into two parts, which can give it a positive information gain. All right. Now, again, it will divide. Let's say this is what you have in the first subset. These information are there in the first subset. Okay. These information are there in the second subset. Okay. Again, it will divide further. Right. So now what can it do to divide further? Again, it can use either temperature or humidity, anything. Or wind speed, temperature, wind speed, anything. So what can be the best parameter so that a pure subset can be created? What is a pure subset? A subset in which all of them belongs to single category. Okay, a subset in which all of them belongs to a single category. That is called pure subset. Alright. So if I see temperature value is humidity value, if I check. $30, $22. Okay, fine. So now we can just use over here. Wind speed lesser than 30. Wind speed lesser than 30, true and false. Right. So what happened? This one, 27, 22 and no. 27, 22 and no will be over here. Rest will be over here. Right. Like yes, yes, no, yes. Okay. This will be over in the other side. And this will be on the other side. Okay. Same way here in this case, I can do what? Wind speed. Wind speed higher than 40. Okay. So if wind speed is higher than 40, then 36, 45 yes. Okay. Rest no will be over here. Right. Now let's calculate the Gini index once again. Okay. So to calculate it, here we will calculate 1 minus probability of 1 is what? 0. Probability of 0 is what? 1 square. That will be equals to what? 0. 1 minus 1 will be 0. Right. Here it will be what? 1 minus, what is the probability of yes? 3 upon 4. What is probability of 1? No. 1 upon 4 square. That would be equals to 1 minus what is 3 upon 4? 0.75 multiplied by 0.75, that is 0.56 plus 1 upon 4, 0.25 multiplied by 0.25, 0.0625. That would be equals to 1 minus 625. That would be equals to 0.375. Right. If you calculate it over here, 1 minus probability of 1 is 1, probability of 0 is 0. So this is it is equal to 1 minus 1, 0. This is what? Probability of 1 is 1. So probability of 1 is 0. Probability of 0 is 2 upon 2. 2 upon 2 is 1 square. That is equals to 0. So whenever you get a pure subset, right, Gini index becomes 0. And if it is impure subset, Gini index is what? Non-zero. Again, if you have to calculate the information gain, let's calculate the information gain. Information gain will be equals to what? For here it is 0.48 minus weighted sum. What is weighted sum? 1. It is having what? 1 upon 1, 2, 3, 1 upon 5 multiplied by 0 plus 4 upon 5 multiplied by 0.375. That would be equals to 0.48 minus, what is 4 upon 5? 0.8. 0.8 multiplied by 0.375, 0.3. That would, because this thing is 0, this thing is 0.3, so this is 0.18. Again, information gain is positive. Information gain is positive, that means this diffusion is good. Right. Now what happens? This can't divide further, this can't divide further, this can't divide further. Only you have to divide this thing. Right. So again, I'll do what? I'll just take it. Okay. So this will be further divided. All right. Okay, this will be further divided. Now, how it will be divided? We have 4 samples. These 4 samples we have. So what we can do? We can just use over here temperature or humidity. What? Temperature 27, 20 for the years we have 27, 31, and 25. But there is a no between 20. No, it is. If I use lesser than 30, so lesser than 30 is no one, lesser than 35, we have these 2 guys. Or higher than 28. Again, lesser, higher than 28, 27. What should I do? 25. If I use 25, 26, 27, 28. Temperature lesser than 28. Okay, fine. So here, temperature is lesser than 28. Okay. If I use temperature is lesser than 28. Okay. So what happened? We have these 2 entities lesser than 28. Both are yes. Right. So in this case, we have yes, 2 yes, and in this case, we have 1 yes and 1 no. Right. So this will be further divided, kind of thing. Right. Because this will, here Gini index is 0. The formula is what? 1 minus, it's like 1 square plus 0 square, that is 1. That is 0. Right. So whenever it is a pure subset, the division stops further. But if it is not a pure subset, it will keep dividing itself. Right. So based on this tree, if I have to predict what is it? 30. 30 is what? 30 is lesser than 32. So move in this direction. Right. Then here wind speed is lesser than 30 or higher than 30. It is higher than 30. So move in this direction. Okay. Now over here, temperature is what? Lesser than 20. So the division I am using. What division? Let's say wind speed lesser than 37. So wind speed lesser than 37. So here in this direction it will be no, and here it will be yes. Right. Now my wind speed is what? 42. 42 is what?
Not visible.
My screen is not visible. Just a minute.
Just know it when. So.
Okay, I'll just share on screen. Is it visible?
Yeah, it scans.
Yes, sir.
Okay. So now here the process is like this. See, let's say I have this one to predict. Okay, 30 and 42. So 30 is what? Lesser than this 32. So as 30 is lesser than 32, that means we have to move in this direction. Right. Now here, next thing I have to compare wind speed, because here wind speed is there. Wind speed is lesser than 30. No, it is not lesser than 30. It is higher than 30. So move in this direction. Okay. Then again, here I'll come. Temperature is lesser than 28. No, it is higher than 28. So move in this direction. Okay. Here, wind speed is lesser than 37. No, it is not lesser than 37, higher than 37. So move in this direction. And here it is finally yes. So the outcome of this guy will be what? Yes. Right. So there are two things which are important. One, the impurity index that we are calculating through Gini index. Okay. If the Gini index is 0, it will represent a pure subset. If it is not 0, that means it is not a pure subset. It is having multiple categories. Like the first node is having multiple categories. So Gini index is non-zero. We divide it based upon certain criteria. Each of the node will get their Gini index. Right? Each of the node will get their Gini index. Like this is a Gini index of the first node. This is a Gini index of the second node. Okay. Using the Gini index of each node, we will calculate the information gain. Okay. Information gain should be positive. Then only that division criteria will be acceptable. Next, it will further divide it. Okay. When it will further divide it, out of 4 nodes, 3 nodes becomes pure subset. As they become pure subset, that means in those nodes, all the samples belongs to single one category. Okay. As they become pure subset, they will have the 0 Gini index according to the formula. 1 minus probability of 0 or probability of 1, right? Or you can say probability of 1, probability of 0. So probability of 1 is what? There is no 1, there is no yes. Here we don't have any yes, so probability of 1 is 0. And probability of no is what? There is only one no, so that is 1. So here it becomes what? The Gini index 0, here also Gini index 0, here also Gini index 0. That means they will not further divide. It will further divide because Gini index is non-zero. It is non-zero as well as if you calculate the information gain, that means previous Gini index is 0.48 minus weighted sum of Gini index over here. Weighted sum of Gini index over here. That is 0.3. So it is what? Positive. That means this division is acceptable. Right. So this division is acceptable. Then it will further divide, and at the end you get the pure subset. This is how decision tree is formed, and using this tree, your model can make the predictions. Am I clear?
Got it.
Okay. So let's try to implement this thing. Okay, so for this I need a data. First I'll take a simple data. So that we can understand it. All right, let's take this data. It is not so simple, but it is not so difficult as well. Okay, so it is a data for intermediate level, so that we can understand a lot of concept over here. All right. So this is a data which is representing the whether the loan should be approved or not approved for a particular person. The information is like loan ID, gender, married, okay, dependents or non-dependents, how many dependents are there, education level, whether the person is employed or not employed, applicant income, co-applicant income, what is the loan amount term, what is the loan amount, what is the loan amount term, okay, what is the credit history and property area, like urban, rural, or whatever it is, like semi-urban kind of thing. So first of all, I'll remove the loan ID, which is not so important to predict the loan status. So df.drop. Done. Okay. Now we'll just few thing we'll check over here, like df1 dot is na dot sum. Okay, so we do have some null values over here. All right, so we'll just try to identify the numerical and non-numerical data columns, right? So that we can treat the null value properly. So df1 dot select d types, okay, include is equals to number. These are the numerical columns. Okay, so I can just use over here numerical columns. Okay, then we have the non-numerical columns. There's the non-numerical columns over here, right? Now let's see df1 non-numerical columns. dot is NA dot sum. That means in this case, how many missing values do we have? So gender, married, dependents, and self-employed. Okay, so check each of them. DF1 gender dot unique. Okay, same way married dot unique. Dependents dot unique. DF1 self-employed just to understand what are the unique values exist over there, right? Let's print it. Okay, so we find male, female, yes, no, okay, fine. So these are that means, and the number of missing values are also not that too high that it will create any kind of biasness. Let's check the shape of your data. shape is just 614 and the number of unique values are like 13, 15, this thing. So it will, if I fix these missing value with any single value, it will not create a huge bias, right? So what we can do, we can just use the majority of a mode value, a value which is most repeatable, right? Like for example, in case of gender, okay, male is mostly present, right? So wherever it is missing, we can replace with male. Already it is biased. So again, if I fill these 13 values with the male, that will not create a huge difference. Okay, because data is already biased, right? So we can use those 13 gaps with the male only. Same way for the mad and all. That means we can calculate the mode value for each of them. Okay, let's say print df1 gender dot mode, and the mode is present at index 0, so just pick index 0 over here. This is male, right? Same way I can do for others. Gender, and after gender it is married. I don't know what happened to this collab since last 1-2 days. Connecting, disconnecting is going on. Dependents and thereafter self-employed. Okay, so these are the mode value. So wherever the missing values are there, I can just fill it. Dot fill in the mode value that we have. So for gender, it would be male. Okay. Then for married, then for dependents, then for self-employed. All right.
So the self-employed one, the mode is the square brackets is 0.
Okay. Now let's check the numerical columns. Okay. Dot is NA dot sum. Okay. So I have these two columns, these three columns where we have the missing values: loan amount, term, and case history, right? So I just try to analyze their mean and median. So DF1, loan amount dot aggregate mean and median. Okay. Just to understand whether they have some sort of outliers or not. If there will be outlier, the mean and median will have the wide difference. If outliers are lesser or there is a lesser possibility of outlier, the mean and median will be very close. So let's say loan amount, then loan amount term, then credit history. All right. So we find that for these cases, median can be the good value because mean and median having little wide difference, and there is a possibility of outliers. So to fill the gaps, we can use median, right? So let's say loan amount term dot fill NA. This mean and median concept already I covered for you. In case if you have any doubts, you can let me know. Okay. So here median, because median is something which is not affected by outliers much. Okay. Done. So now df1 dot is NA dot sum. So it is done now. Now let's check the data frame. Okay. So now what we will do, we'll sum up applicant and co-applicant because it's a total income, right? So just try to do few changes in the data. It is actually the income, right? So we need to convert them into just income. We can sum them up into a single, single feature instead of using them separately, right? So we can use df2 is equals to df1 dot copy. First of all, create a copy of your actual data. Right. Now df2 applicant income. Generally, this is a process we do in case of loan thing. We just consider both of them as a overall income, right? Okay, so I can just make it a thing like income. And this income I can add it over here 0, 1, 2, 3, 4, 5. At the fifth index I can add. So df2 dot insert. Okay, insert is a method which is used to insert a data column. Right, let me write it into a comment. Insert a method to insert a data column into the data frame. Right. So df2 dot insert at index fifth I want to insert. What I want to insert? I want to insert income, and the value of income is income. Okay, so now let's say df2 dot head. Alright, now I can remove this applicant and co-applicant income. Right, so df2 dot drop columns is equals to these two columns we don't want now. Done. Okay, now we have to convert the non-numerical things into the numerical form, right? So what are the non-numerical columns? We have these are the non-numerical columns, non-numerical columns. Okay, so these are the non-numerical columns which needs to be converted into numerical form. So for converting into numerical form, we have to check whether they are nominal or ordinal, right? So what we can do for column in non-numerical column, just take each column one by one. Okay, so these are your columns which is containing non-numerical data. Okay, how this thing came? Already we have created it over here. If you I'll show you, see non-numerical columns we have already created somewhere. Here we have created. Non-numerical column is what we have just selected. Select d types number. So it is just selecting the numerical data and it is selecting, sorry, it is excluding the numerical data, exclude number. Here include number. So we already exclude the numbers, so only non-numerical picked up and we check the column names. So these are our column names. Right. So now what we can do, if these are your column names, I can just pick the data from here. Dot unique. So from each column, I want to check the unique values. Okay, from each non-numerical column, I want to check unique values. Right. So here most of them seems to be ordinal. Male, female, just two categories 0, 1. No years, just two categories 0, 1. This is already 0, 1, 2, 3. Just make it 0, 1, 2, 3. Graduate, not graduate. This is also ordinal. Okay, we can set into order. Not graduate first, then graduate. Or two category 0, 1. This is also two category 0, 1. This is also ordinal, like rural, then urban. So rural, semi-urban, then urban. Right? So all of them are ordinal. So what we can do, we can simple do the label encoding. Right? We can just do the label encoding over like df2 gender dot map zero one. Okay. Thereafter df2 married, then df2 dependence education is done, and thereafter he was self-employed. Thereafter we have the next one, df2. Property area. And then df2. Bonus status, right? The last one, right? All right. So now it is done. Okay. So it's like I'll just execute it. So df2 dot head. Most certainly everything is now numerical. Okay. Now you can just create x is equals to df2 dot drop. Columns is equals to loan status. And y is equals to loan status. Okay. Now I can split from sklearn dot model selection, import, train test split, thereafter X train, X test, Y train, and of the test. That would be equals to what? Your split, right? Okay. And thereafter we can just create the final model dot tree, import decision tree classifier. So model A is equals to done. And then we fit the data. So model A dot fit X train, comma Y train. So once we fit it, it got trained. Now we'll calculate the accuracy. So for calculating accuracy, model A dot score X train, comma Y train. Okay. So if you see on the training data, it is 100% accurate, but test data, it is just 67% accurate. What this mechanism is called? What do we call it? If a model behaves like this, that means a model which is showing a kind of a very high accuracy on the training data, but on test data the accuracy is not up to the mark. So what this mechanism is called? Can anyone tell me? This is called overfit, right? This is called overfit model. That means a model which almost memorizes everything which is given as a training data. Okay, a model which memorizes everything which is given as a training data, but outside the training data, if anything is asked, it fails to answer. Am I clear? Now, how to handle this overfit? So, before we handle this overfit, we should know what's the what this overfit actually means, right? So, or why this overfit actually happens? Why this happened? So, see, here is something that we import the algorithm to build the model. Okay. This is an algorithm we import to build the model, like usually imported, right? From sklearn.linear model, from sklearn.neighbors. So here we are importing from sklearn.tree. Same thing we can use over here from sklearn.tree import plot tree. All right. And in the plot tree, I'll feed over here model A. All right. So you can see the tree over here. Right. Now this tree is not that much clear. Let me just try to make it more clear. We'll import matplotlib .pyplot as plt. And I'll define the plt dot figure size payload figure size is equal to, let the figure size I'll decide as 16,8. Okay, so if I use matplotlib to create a layout, and within that layout if I plot, it will be a little better, right? So now if you see over here, our tree, it's a very big tree, right? So many nodes are there, right? So what it actually did, even a particular node each containing a single sample, it is dividing it. Like you can see here, we divided it till the time we are getting a pure subset. So in the process of finding a pure subset, this is a node which is containing just one sample. This is a node which is containing just one sample, right? We have just two category over here, yes or no. But to decide two category, how many leaf nodes do we have? Leaf nodes means what? The end node, the last node, right? So just to decide whether loan should be approved or not approved, how many nodes do we have? If you check it over here, see, here is a leaf node, here is a leaf node, leaf node, leaf node, leaf node, leaf node, the decision making nodes. That's a huge. Even so many nodes over here may be containing just one sample, right? That means for the known data, if you just consider the known data, so for the known data, your model actually knows the place of each and every entity used for training. Okay, for the known data, your model knows the place of each and every entity, each and every sample, like which sample belongs to each node. That's why it becomes 100% accurate. Right? Model is what? 100% accurate for the training data, because for the training data, it knows that which sample belongs to each node. Correct? But if I will control it, let's say I'll make it maximum depth is equals to 1. Okay? So you can see now over here 80%, it is and then you see the tree, it is just that one. On what basis is X8? What is X8? You can use over here plot tree feature names is equals to x dot columns. So it just divided based on credit history. Okay, it is using only one information which is called credit history, right? Okay, it is using just one information which is called credit history. That is very important, right? Because this information may be giving the maximum information again. So now if it is divided, you can see over here that on the left hand side, we have all non-approvals. That means 62, that is 0. That means if the credit history is lesser than 0.5, the loan should not be approved. And if it is higher than 0.5, the majority are approval, so loan should be approved. Okay. So how much depth we should consider? Depth we can consider over here like depth 2. So with the depth 2, what we have? You can see still it is not overfit. If I am using a depth of 2, then also it is not an overfit model. Okay. It has further, this is a depth of 2. Okay. So, we have to use this hyperparameter in a way that my model should not get overfit. Right. So here it is not overfit. So depth of 1 or 2 is working good over here. Am I clear? I'm sharing this file with you. Please have a look. Go through the things. Let me know if you have any doubts. Then we go ahead for the next part. So now we'll just try to check its performance matrix. Already we checked the classification report. Let's say from sklearn. Some sklearn dot what should I take? Metrics. Import classification report. So print classification report. I'll just compare the actual label and the predicted label. So model A dot predict. So it is biased for category 1. That is good thing. Okay, obviously I want to predict non-approval over here should be higher. Okay, non-approvals. We can't approve to the person who is not suitable. So like in last example, true positive rate required higher. In this example, true negative rate should be higher. Isn't it? Because I can't approve to a person who is not eligible. Right? Otherwise it will be a financial loss, right? But here true negative rate is poor. Why it is poor? Because if you look at the data, y dot value, majority of them are yes, isn't it? So what we need to do, we need to work on oversampling, isn't it? So here I can just use, it is a biased data. So from IMB learn dot oversampling import SMOTE. Okay, and thereafter oversampling object SMOTE, and thereafter ROS dot fit resample. X comma Y, right? So we will have XR comma YR. Okay. So when we do it, YR dot value just wait a minute. Okay, so now both become same. Earlier This is lesser in number, no is lesser in number, now it is 422. Alright. Then we can use over here XR, YR for the splitting. Accuracy slightly came down, but we have test accuracy is higher. Okay, if I'll increase the depth over here, let's say 3, then both are fine. This is my current tree. Obviously data increases, so depth of tree is also increasing. It is close to 75%. Now biasness is handled. Still on the test data, you can see no is little bit less accurate. Even after handling the biasness through oversampling. So suggest me what else can we do to increase the accuracy of no?
Undersampling.
No, undersampling will reduce a lot of data. We can tune the class weights, isn't it? Here class weights. We have two classes, right? So I'll say that for category 0, the weight can be double the weight of class 1. Okay, if for class 1 weight is 1, then for class 0 weight can be 2. I'm just making it double. Class weights of class weight. What happened? Oh, it should be df2 over here, right? So here for class 0, we increase the true positive rate. All right. Both becomes close to 80%. All right. Now one more thing. These are called hyperparameters, right? So sometimes it is difficult to decide the hyperparameters. All right. What are the other hyperparameter this is having? Let's check. Decision tree. So you can see these are the hyperparameters. Okay. When we talk about the criteria, I told you about entropy. There are two more criteria are there. Sorry, I told you about the Gini index. Okay, I told you about the Gini index. There are two more criteria, which is called entropy and log loss. Right? They also do the same thing. Only the formula is different. Okay, like for example, if I talk about entropy. Okay, so what is entropy? See, if you see the tree is showing what the Gini index value, right? Gini index value. If I will use a criteria as entropy, Okay. You can see it is showing what entropy now. Okay, it is showing what entropy, but as a pure subset, entropy is 0. So here also rule is same. Entropy will continuously decrease as you are moving towards the pure subset. Okay, and here also it will try to identify the information gain, just like earlier. Okay, weighted sum of entropy and all. Only the formula is different for calculating entropy. Okay, Gini index formula is different, entropy formula is different, right? So what is entropy formula? It involves actually log this is a formula for entropy. Okay, sum of minus probability of any category log base 2 to the probability. Like how is it calculating? It is calculating like this. See, we have 9 upon 14 log base 2 9 upon 14, isn't it? You can see over here, plus 5 upon 14 log base 2 5 upon 14. Okay, this is how entropy is calculated over here. All right. So entropy will also do the same thing. It will help you to identify the pure subset. This is also one of the impurity parameter. Okay. And the third one is what? Log loss. So log loss is also an impurity parameter. This is a log loss formula. Okay. So the formula is different, but the purpose is same. Okay, to find out a pure subset. All right. All right. So here, now what are the other parameters? Thereafter, split up. Split up, we can choose best or random. That means whether a particular column and it is picking up to split, whether it should be based on the best information gain or it should be picked up randomly. Right. Best is little slow, random is fast. Right. Like for example, when it is splitting over here, it is splitting based on credit history. Why? Because out of all the column, credit history is best, which is giving the maximum information gain. Next time it is using loan amount and married because they are best. Okay, so every time it is choosing up that particular column which is giving the maximum information gain. If I use random, then it can pick any random column and divide it. Maximum depth already we had seen to control the depth. Minimum sample to split. Okay, so what is your minimum sample that you want to split? That is called what? Minimum it used to be 2, right? Like for example, in any particular node, if it is having 2 samples, it will split. Okay. So to control the overfitting, we can say that no, minimum sample should be at least 10, at least 20. That means if a node is having lesser than 20 samples, let's say 19 sample, it will not split. Okay, we can control it, right? Minimum samples in a leaf by default 1. Okay, we can say that no, minimum samples in a leaf can't be lesser than 10. So any leaf node is a what? Last node. Leaf node is last node. So last node can't have a value lesser than 10. All right. Minimum weighted fraction in the leaf. Okay. Minimum weighted fraction means the minimum weighted fraction of the sum of total weights required to be a leaf node. That is kind of a ratio between both the category. Maximum feature that you want to use. Okay. For the base split, random state, maximum leaf nodes that we want. How many maximum leaf nodes do we have right now? We have 1, 2, 3, 4, 5, 6, and 7 leaf nodes. Okay. If I say over here that I only want maximum leaf nodes, I only want, let's say, 4 leaf nodes. So you can see we have only 4 leaf nodes over here. Okay. But it's little underfit. Okay. We can just try for, because this accuracy is going more than 10, so I can make it 5. I can make it 6 as well. Going good. 7. 7 was best actually. 8. All right. Okay. Then we have the maximum impurity decrease. How much minimum impurity decrease you want according to this formula? Class weight, just to balance the things. That had already been used. So these are the different hyperparameters that we can try. But how to find out the best hyperparameter? So to find out the best hyperparameter, there is something called grid search CV. Okay, what? There is something called grid search CV. Grid search CV. Right? So what is this grid search CV? So grid search CV is like getting a grid of parameter and then let the algorithm find out the best hyperparameter. It's a powerful tool in machine learning, particularly in hyperparameter theory. Allows for systematically finding the best combination of hyperparameter. Okay, that is just the highest model performance. That is called grid search CV. Okay. So grid search CV stands for cross validation. First, try to understand cross validation. Okay. So first we'll try to understand the word cross validation, and then we'll try to understand grid search CV. Okay. Now, what is cross validation? Cross validation is a process in which we do what? We basically let the model validate its performance on different data splits. Okay, this is called cross validation. Right. That means we let the model do what? Split the data for multiple times. It's showing very small actually. Okay, so we let the algorithm or model split the data for multiple times and evaluate its performance on the different splits. Like how it is performing on the first split, second split, third split, fourth split. What it means? See, when I will split this data once again, as of now accuracy is what? 76, 78. Again I'll split it. Again train it. It changes. Right? Again I split it. It changes. Right? So every time I split the data, the information in the train and test is different. That's why final performance is changing. Right? Now I am unable to say like what should be the a value accuracy that I can quote, because every time it is changing, right? So what can we do? We can split it for 5 times, 7 times or 10 times and take the average of all the performance. Okay, that means let's say 5-fold cross validation. Okay, so from sklearn dot model selection import. Let me check the library actually. Cross validate. Okay, still let me check the library because I'm little I missed the name of library. Over here, sklearn cross validation. So we'll get the library. It is sklearn dot metrics or model selection. That's what I'm missing over here. You should know the concept. The library anyway, you can find it from its documentation. A lot of time. Okay. This is what we got. Just copy this whole thing from here. Paste it over here. Okay. Now here, CLF is equals to model B is equals to okay, then scores your model B, okay, and 5-fold cross validation I want to do, then I will get at the scores. Right. So it has given me the test accuracy. Minimum is 71 and maximum is goes up to 82. right? I can use 10 as well. And generally we take the average of scores, right? So these are the print scores. It is close to 80%. Okay, so this value is more, we can say that 10 times when we test our model on different split, average score comes out to be 79.3%. So this we can trust more, isn't it? This is called what? Cross validation. Okay, what it means is split data for 5 times and evaluate its performance. Next is called grid search cross validation. Grid search cross validation will do what? It will cross validate as well as tune these parameters. Right? Let's say I'm not sure about the parameters. So what I do, I just define the parameters over here. Alright. So what are the parameters we will define? Let's say if a criteria and other things are there. Right, let's say criteria. So in that criteria, what I have to give? Let's say whatever the criteria that I can give it. Okay. All right. Next, a splitter. Next, maximum depth. Let's say 2, 4, 6, 7. Next, minimum sample in the lead. Two, 5, 7, 10. Okay, thereafter next, minimum leaf nodes, maximum leaf nodes. Obviously, I can't try and list each of them because that will take a lot of time. Okay. All right. These are parameters. Next, what we define, we have to just call over here the grid search library. So from sklearn dot model selection input grid search CV, right? All right. And then we will define over here model C is equals to decision tree classifier. Then I define grid model is equals to grid search CV. And here I have to pass few things. First, I have to pass the model, that is this guy. And second, I have to pass the parameters. Okay. And then grid model dot fit x, y. Okay, I can just check it. So it will just try and test each possible combinations over here. Okay, it will just try and test each possible combination for you and to give you the best estimator. So this is your best estimator it has given to us. Okay, that means I can just search over here grid model dot best params. So the best params we are getting it like this, or I can also use best estimators. Okay. Now I want my model to train on these estimators. So what I can do, I can just define model after grid is equals to decision tree classifier okay, and I can define the parameters okay. Criteria it is saying what? Entropy maximum depth it is saying that you should use 2. Okay, maximum leaf node it is saying that you should use 3. Minimum sample for the leaf it is saying what? Two. Right. Now based on this, let's try to train and test. Okay, and then accuracy. Almost done. Okay, it is close to 73 to 72%, and then we can also check the classification report, right? Okay, so for the classification report, I have to use this particular model. Okay, so for the train, it is going 81%, that is good. That is non-approvals of the loan. True negative rate over here is good. So depending upon the situation, like in the last situation, it was true positive rate required higher. In this case, true negative rate requires higher because here the non-approval should be predicted with high accuracy. Okay, approval if it is predicting with low accuracy, it's fine. Non-approval should be with high accuracy because no bank wants that loan should go into NPA, right? So non-approval should be with high accuracy. Right, but non-approvals are having lesser data, so we use oversampling. But oversampling was just maintaining both of them at an equal stage. Then we use class weight management. We increases the class weight for category 0. So now it is at higher accuracy. Overall, it is a good model, having close to 75% of accuracy. Okay, so you can see we did the hyperparameter tuning using grid search CV. So hyperparameter tuning is one of the steps that many algorithms you have to use to find out the best possible hyperparameter. Just have a look, go through the things, finish it, then we will try to work on random forest classifier. Okay. Please finish it. You can take your time. Once done, you can let me know so that we can proceed. Okay. So next, random forest classifier. Why I pick this thing all together with decision tree? Because random forest classifier is exactly similar to decision tree. Okay. Because tree, when so many trees used to be there, it creates what? Forest, right? So in random forest classifier, what we do, instead of just depending on the single tree like this, okay, we let the model create multiple trees, right? Instead of single tree, what we say, we ask the model to create over here multiple trees. Right? So it would be like this. Let's say this is one tree, right? One decision tree. Okay, now we have one more tree. Okay, so now it's like we have 5 trees. Right now, I can just form the 5 more trees. Okay, so now what happened? If I will form the multiple trees, what is the benefit? The benefit is like each particular tree, if I form a single tree, then a limited amount of features are used. Out of every feature, how many features it is using? It is using 1 feature, 2 features, 3 features. Then again, gender 4 feature, loan amount again loan amount. So 4 features it is using. Okay, it is using only credit history, loan amount, married, and gender. Still, it is not using 7 out of 7 features. Right. So there can be, multiple possibilities and multiple combinations are still left. So we can form multiple trees, right? And each tree can form their structure using different combination of feature. Okay, here some different combination of feature can be used. Here some different combination of features, right? So now, if I will ask the model to predict something, so that model will do what? Will just ask, that model will consider multiple trees to predict. That means this tree will make some prediction. Let it be 0. This will be let's 0. This is let's say 0. This is let's say 1. 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 Right? This is let's say 1. This is let's say 1. So majority of them are about 1. So final prediction will be 1. Right? So when you form multiple trees, the model will just consider multiple trees and then what majority of the trees are predicting. That is a final prediction. For example, in this case, if I have to predict, let's say if I have to predict it over here, I will take what? X test value. Okay, let me take any random sample. Okay, it's a sample number 10. Okay, then this model I want to use. So here is a single model which is predicting the outcome as 0. Okay, here is my single model which is predicting the outcome over here as 0, right? isn't it? That means loans should not be approved. But if I will use random forest classifier, model R is equals to, okay, and then here I'll feed one parameter called number of estimators. Let's say I want to build 100 trees, okay, and rest of the parameter I can use as it is. Okay, thereafter model R dot fit okay, thereafter print model R dot score extend comma y tray. Accuracy over here came down drastically. That means I have to do something. X test. Okay, so the accuracy is coming down, right? Maybe I have to increase these things, that depth and leaf node. So I can use grid search CV, or I can let's use Gini over here. And say maximum depth. Let me remove these parameter. Only depth will control everything. Is improving a bit. No, it is not improving. So almost it gets stabilized over here, right? And if I not use class weight, that is good, because random forest actually, kind of maintain or tune the parameters on its own. So it is goes to 80%, right? Now let's try and test other factor like classification report, because it works on the voting, right? So as it works on the voting, what majority of the tree predicted? It works on what? What majority of the tree predicted? So number of hyperparameter we don't require that much, right? That's why you can see when it changes, remove the hyperparameters, this thing. Now for category, let's try to handle the category 0 accuracy. Equals to 0, it's a 1.5 times. The 1 is what? 1. Okay, so not exactly I'm making it down, but I'm making it the way I'm increasing by 1.5 for category 0, because category 0 is less than sample. So it is trying to be more balanced. Let's make it 1.75.
So your screen is not visible.
Screen is not visible. Just a minute. So I'm trying to make this category last week. I'm trying to tune it so that for category 0, that is for loan, non-approval of the loan, my accuracy can be better. So what we did, we just formed 100 trees. Instead of just one, with the random forest, we can form 100 trees. Again, whatever you want. My screen is visible now. You can see my screen, right?
Yes, sir, it's visual. Yeah.
Okay. So now for category 0, it is highly accurate, 80% accurate. Overall also 77. So this is a good situation we got. Right. So what I'm telling you, we created multiple models. Okay. How many models? 100 models. Right. Now what majority of the model will predict, that will be the final prediction. Can you visualize all 100 models? Yes, we can visualize all 100 models. See, I'll just copy this visualization code. This line is for visualization, right? So I can do what? I can use model R index 0. That will give me the first model. Okay, this is the first model. All right. Now I want second model, right? This is your first model, which starts with credit history. Model 1. So this is second model. That starts with, don't know what it is, not properly visible, but it must start with something, but not credit history, right? So it is using different combination of features, right? Then let's say model 2. All right. Right. That means what? If I have a data to predict, let's say this is a data that we use for the predictions. So you can just change the index value over here and it can goes up to 99 because we have 100 models. So up to 99 value you can use it over here, right? 99 trees can be there and then 100. 100 will not work, right? Because total we have 99 trees. So 100 trees, so 0 to 99, 100 trees, right? Now let's say I want to predict. So model R.predict. So this is a final prediction, that is what majority of the tree predicted, right? Now what we can do, we can, if I want each tree prediction to look after, so for tree in model R, print tree 0 dot predict. So tree dot predict each tree prediction I want. Or you can say for no, not like this. For I in range 0 to 100. Okay. Model R index I dot predict so this is a prediction made by each tree. Okay. So this is a prediction made by seed. Some of the samples it is predicting, sometimes it is also predicting 1. right? If I want to store all the predictions, so this is overall prediction because majority is 0, right? So all predictions is equals to a blank list, and I can append all the predictions over here. Dot append now I can do it np dot array all predictions to count how many 0 are predicted and how many 1 are predicted. Dot value counts. Okay, this is not happening. So you can say my model, current model had predicted 96, 0 and 4 times 1. Okay, that means this particular model that we created over here, when I feed a particular sample to predict, okay, when I feed a particular sample to predict this particular sample, okay, that means the 10th sample in test data. Okay, we are predicting on the 10th sample in the test data. Okay, this is your predictions. 10 sample in test data. Right. So overall prediction is 0. But when we are picking up each model one by one, total 100 models and making the prediction. Right. So at the end, 96 times it is predicting 0 and 4 times 1. So overall it is 0. So where it is good, like suppose there are so many situations in which the data is not so much good and quality is not that good. So instead of using a single tree, we use random forest, because instead of dependent on the single model, we make use of 100 models or 50 models. So we can expect a higher accuracy. Here the accuracy is not changing much, I guess. Slightly change here, 81% is there for category 0 or 76%. Here we have 81. It's slightly better. Slightly it is better for category 0, that is for non-approvals of the loan. So model performance slightly improved compared to single decision tree. Right? If I use 10 over here, no, 100 was good. Sometimes 10 is not enough. All right. That is done. So please have a look, go through the things and let me know if there is any question. After this, I have to cover a new algorithm, that is support vector meshing and naive bias. I will not cover that in today's class because otherwise things will get mixed with each other. So in the next week, we'll cover support vector and naive bias. And second thing, we'll also start with the unsupervised learning. So unsupervised learning will take 2 classes most probably, and thereafter, I'm going to go for the next part. Okay.